welcome back. We are here for part 2 of our video series on forces. In this particular case, we're going to take a look at Newton's laws of motion, which all have to do with force in one way or another, and how force interacts with motion, obviously, since they're Newton's law. I know you've heard of Newton's laws of motion before. These are not new. You've had these, you heard these since you were in middle school. So just as a reminder in terms of language. So Newton's first law of motion is what we would call inertia, is that word. An object at rest tends to stay at rest. An object in motion tends to stay in motion unless acted upon by an outside unbalanced force. That's the part they always leave off. But an object at rest tends to stay at rest. Second law is relates to acceleration. Basically, Newton's second law of motion is force equals mass times acceleration. Pretty much that's it. Net force results in acceleration or change in motion. And then the third law is that forces are always found in pairs. You have heard it written this way: for every action, there is an equal and opposite reaction. And that is true, although there's a very common misunderstanding for how that works. So what we're going to take a look at through here is some examples of these different laws of motion and how they apply. And then we'll come back in a follow-up video and do some examples of some math problems that actually take Newton's laws into account when you're doing some solutions based upon his laws. There we go. So Newton's first law, when we're talking about inertia, inertia has to do with systems that are in equilibrium. And now this is an interesting concept for students, because equilibrium means that the forces that are in play are all balanced out. So, right, an object at rest tends to stay at rest, an object in motion tends to stay at motion. However, this does not mean that there are no forces acting upon an object. There could be hundreds of forces acting upon an object, but they all cancel each other out. The net force is equal to 0. And you can see I've got that written at the bottom there. So when we write the phrase net force, there's two different ways that we write it. Just a notation note is that we can put it in two different formats. Let me grab my pen real quick here. My apologies, pen, there we go. So these both are read as net force, and they mean the same thing. When you put it in this notation, this is the Greek letter sigma. And you remember that from math class, meaning the sum of, and it means exactly the same thing here. Delta means subtract, and sigma means add, right? So this is the sum of all of the forces adds up to 0. Remembering that forces are vectors and forces in opposite directions cancel each other out. So again, when we're talking about inertia, things that don't have any unbalanced forces in them want to continue their motion, whatever that is. They don't want to change their motion. That's what equilibrium means. So our friend on the motorcycle over there is not having a great day right now. But people would say that, well, I thought you said an object at rest tends to stay at rest. Yeah, part 2. An object in motion will stay in motion at constant velocity unless acted upon. So here the poor dude's motorcycle has stopped, but he has continued with his forward momentum, right? He is continuing at a similar velocity to what he had done before. He's not curving, speeding up, or slowing down. So that is Newton's first law. Kind of a bummer at that. So a couple of other examples of where Newton's first law may have impacted you in your life. Seatbelts, great example of that. We use seatbelts to try to avoid what happened to our poor friend on the motorcycle, right? If your car stops, you don't. So keeping your seatbelt on you is a way to kind of help you move with the vehicle. It actually helps to violate Newton's first law, if you want to think of it that way. Terminal velocity, by the way, when you're skydiving, at first, when you first jump out of the plane, you are accelerating, and you definitely know that you're following. But after a little while, you achieve something called terminal velocity, where your downwards force and the upwards force of the air equal each other out. And therefore, you almost feel like you're not falling anymore. And you can do tricks and stuff like that in the air, but you just get the feeling of the wind rushing past you, but you don't really get that feeling like you're falling. You almost feel like you're holding still. Movement in space or in zero gravity is definitely an interesting case of Newton's first law, because you don't have the force of gravity. That's the one that's always affecting us, that we forget about, that we're always accelerating things due to gravity here on Earth. But when you're out in space, if you throw something in a straight line, it's going to continue in that straight line forever, or until it gets acted upon by an unbalanced force, like entering a gravity well or something like that, or hitting something else that may cause it to slow down. So again, once you throw it in a straight line, you throw a baseball in space, goes forever in a straight line. That little card trick on the bottom left, by the way, that's that common, like you flick the thing, you flick the cardboard and the penny drops straight down. That is definitely, that's the inertia, right? Object at rest tends to stay at rest. The coin's going to hold still. The card will kind of flick out from underneath that. There isn't quite enough friction to make the coin stick with the card, and the coin drops straight down. And then I put this little picture here on the bottom of those are leaves that were on a trampoline. Actually, I think it was a hammock. But what happens, it was like full of leaves, and then they dropped something really heavy right into the hammock. So the bottom of the hammock fell. The leaves stayed on top, right? Because all of a sudden they didn't have that moment right there where they didn't quite start to accelerate you to gravity. There's just that instant where their velocity was still equal to zero. And that's kind of what that picture sort of represents, a visual of what inertia looks like. And you feel like inertia every day, right? When you can't get out of bed, object at rest stays at rest. So Newton's second law, though, is much more interesting to us in general about physics because acceleration in general is much more interesting to us. So one of the things to keep in mind about acceleration is everything that inertia isn't. So if inertia is balanced forces, then acceleration is unbalanced forces. If inertia is constant velocity, then the second law is acceleration, right? We've got change in speed or change in direction. We're going to really be talking about change in speed here, really more than changing in direction. But this is the case where net forces now do not add up to zero. And when you have net forces that are unbalanced, don't add up to zero, you will always have some sort of acceleration. Now, how much? Well, it kind of depends. How much acceleration depends on the amount of force that you applied and the size of the object that you apply it to. So you may realize that, I don't know if you've ever been shot in the with a BB before, but a really small object traveling at a high rate of speed can really impact a lot of force on you, right? So if you have a small mass with a big acceleration, it's moving quick. That hurts, right? Same thing, you can have a lot of force from a very large object. Doesn't have to be going fast at all. Think about like a fully loaded semi-truck, literally going 1 or 2 miles an hour, crushing you to death, right? Not a pleasant experience. Thank you. I would not like that. Tons of force can be created by tons of mass, or tons of force can be created by tons of acceleration. Those two things work together in concert to create force. So now what is the units of force? Well, if force is mass times acceleration, the units actually follow from that, although we do have a nickname for that. So here's our units. Our units of mass in this chapter are always going to be in kilograms. So again, this is a little bit different, but kilograms are the standard unit of mass in physics. So keep that in mind. We don't use grams. Grams are too small. They're actually a really, really small unit. So we tend to use kilograms as a much more common unit, again, for masses. And then acceleration is meters per second squared. So when we multiply these things together, we get a complex unit. And that complex unit is a kilogram meter per second squared. Well, that's really awkward to write. So it turns out we have another name for this. There's another name for this unit that's actually a lot easier for us to write. And that other unit for us is known as a Newton, a capital N. Yes, named after the guy whose apple fell on his head. Newton's second law of motion, right? And I'm like, why did that happen? Gravity, right? So we also call a kilogram meter per second is the other name for that is a Newton. So we will typically see that if we're using our standard units, kilograms, meters, and seconds, units of force will be represented in units of newtons. By the way, how much is a Newton? An apple coincidentally weighs about 1 Newton. Nice. So that just to give you an idea what those sorts of values are. So how do we figure out what net force is? Kind of moving forward. If we're trying to figure out net force, you're going to see free body diagrams like this a lot. In fact, I'll make you do it for your homework as well, but you'll see free body diagrams like this. It's important to take a look at our force pairs when we're doing this. So we're only going to be dealing with one-dimensional force. So you either have to look at the XY forces or the X forces, or you have to look at the Y forces. And that's what you're always comparing when you are doing net force. So if we take a look at our net forces in the Y dimension, so the uppy downy forces, fancy words, I know. If you take a look, we've got an upwards force, normal force, and the downward force, which is weight, right? This one is Fg, and this top one here is Fn. Now, we know something about this object. If you've got an object sliding across the floor horizontally, its upward motion is constant. It's not moving up or down at all. So actually, its upward and downward motion is actually more subject to inertia. The net force in the y direction is equal to the normal force and the gravitational force added up. You add them up. That's what sum means, right? Well, what are these? Well, Fg is down. So typically we would say that direction's negative and that direction's positive. That's a typical way that we would do this. So if we do this, Fg is actually negative 196 newtons down, and Fn is positive 196 newtons up, which again equals to 0 newtons, right? Net force vertically, it's not moving up or down at all. Its net force in the vertical dimension is 0. But horizontally, we've got some other forces. So now I'm doing my net forces in the x direction, horizontally, right? I've got two forces. I've got friction force, Ff, and I have applied force, Fa. So in this particular case, let's call to the right positive and to the left negative. Again, we have to define our coordinate systems both directions. So if we do this, then our friction force is in the negative direction. And that's almost always going to be true, that our friction force would be negative 20 newtons. Friction fights the direction of motion, usually. And our applied force is 60 newtons, and that's in the positive direction. So again, math on this, not super hard. Our net force here, net force is equal to 40 newtons. And it's positive, which means that 40 newtons net direction is to the right on the screen if I point it backwards. So we could figure out, we know our object is going to be accelerating. This direction is going to be the net force. So I'm going to erase that FG there real quick if I can get it out of the way. You, buddy. Out. So when we do our net forces, every time it goes back to the wrong pen. Come on, give me my other pen. Or whatever. My net force, which is going to the right in my x direction, is going to be accelerating in that same direction because that's where our net force is happening. If a net force was going the other direction, it would be probably what we would call decelerating, slowing down. So let's take a look at some examples of adding up some net forces. So here you go. You might want to hit pause here and take a look at how these work, but your job is to figure out what the net force is for each one of these, and therefore determine the direction of acceleration. The math on this is actually really, really simple, right? Net force equals mass times acceleration. We're only going to be talking about horizontal motion here, so we really don't care about the up-down dimensions at all. We can assume that all of those are 0. So if we do this, what's our net force? Well, our net force here, we've got -3 to the left. I guess I needed a color that you can read, huh? Come on, give me a pen. Let's do this one. We've got -3 to the left and +9 to the right. So that means my net force has got to be that direction. Well, it would be +6. +6, right? So could we figure out what our acceleration is here? Yeah, net force equals mass times acceleration. We can plug our numbers in. We could sit there and go, all right, net force is +6 equals 2 kilograms, because that's our standard units, times A. So what would our acceleration be here if we divide our acceleration equals 3? +3. In other words, it's increasing its speed to the right. How about in the second one? If we take a look at this one, we've got the same net force here, right? Net force is -3 and +9. So our net force is equal to +6, in other words, positive to the right, which equals mass times acceleration. Now our mass is 3 times A, so our acceleration here is equal to 2. So again, heavier object with the same net force is going to accelerate more slowly. You know that. If I have a heavy object and a light object and I push them the same amount, the light object's going to go faster. Nothing new there, right? Okay, let's take a look at B. Here we've got a 9 Newton force to the right and nothing pulling it to the left. So now we've got 9 newtons, right? 9 is our force, equals 3 times acceleration. So here our acceleration is also equal to 3. That would work really fast. That makes sense too. Now there's no fighting force. There's no like friction or something like that. That's fighting our force of motion. Similarly, I know you can figure this one out right now, right? Now I've got a 3 Newton force on a 3 kilogram object. Our acceleration is not going to be very big, right? I've got this bigger mass. I have a lesser force. F equals ma. F equals ma. 3 newtons of force equals 3 kilograms of mass times acceleration. Our acceleration here is equal to 1, +1. It's speeding up, but it's not speeding up very fast. And then we'll do I'm going to do this last one here. I'm not even bother with E. I know you can figure it out. For F here, 3 newtons to the left is negative. 6 newtons to the right is positive. Again, net force equals mass times acceleration. Our net force here is +3 newtons. Again, to the right. That's what that means. So 3 equals mass is 3 times a. In this case, our acceleration is also equal to 1. So these two boxes right here, D and F, these guys have the same acceleration. Okay, again, you got to look at the net force to determine what your acceleration is going to be. A positive 3 newtons to the right, and that's it? Or do you have a pair of forces that's adding up to 3 newtons? So again, net force equals mass times acceleration. Okay, an application of this is kind of an important one that gets hidden, and that's why I'm taking a moment to bring this up, is that one of the applications of Newton's third law, F equals ma, is the concept of weight. Now, weight and mass are not the same thing. Mass is the amount of atoms. It's the amount of stuff that's in your body. Weight is a force. Okay, weight is due to the acceleration due to gravity on your mass. So we would write it this way. If F equals ma, and I want to talk about something's weight, now we would say Fg, this is called weight, equals your mass times acceleration due to gravity. Remember I said that acceleration due to gravity a lot of times is abbreviated with g? Well, this is our 9.81. That's what that is. So if you want to figure out what your weight is, you simply multiply your mass times acceleration due to gravity, and you get your weight in newtons, and that's kind of important. So if I weighed, say, 70 kilograms, I would multiply that by 9.81. 70 kilograms, by the way, is about 140 pounds, just to give you an FYI, times 9.81. So this thing would weigh 70 kilograms, or sorry, its mass would be 70 kilograms, but its weight would be 686.7 newtons. Okay, again, so it's almost like multiplying it by 10 is a really good guess. So if you want to see what your actual weight is, similar to your mass times 10. Be careful, though, in problems. Again, you're always having acceleration this direction due to gravity, always. So therefore, if you have any sort of mass whatsoever, the weight of that object is simply going to be m times g, gives you weight. Now remember, weight is in newtons. That's how you can tell. Mass is in kilograms. Weight is in newtons. Weight is a force. And that's the thing to kind of keep in mind. We'll do some example problems when we get back to this, but I just wanted to bring it up kind of in here. Okay, our last one is Newton's third law. We'll deal with Newton's third law more in some of the problems that we've got coming up. But Newton's third law, you've heard that for every action, there's an equal and opposite reaction. So forces typically always exist in pairs. So, and that's the joke that's on the board. You can't touch the ground without the ground touching you. Every time you exert a force on something, it must also be pushing back on you and somehow. Now, these are equal and opposite. So if I push on the table's pushing on me. I know it's kind of weird to say that, but there's always pairs of forces in the world. And we start to talking about pairs and pairs of forces as we start trying to analyze more complicated diagrams. So again, for every action, there's an equal and opposite reaction. So where do we see this? All of these are just sort of epic pictures of action-reaction pairs. Now, a lot of times fail videos come out of misunderstanding Newton's third law. For example, our friend falling out the boat or our friend falling off the paddleboard. You're pushing forward on the paddleboard and the paddleboard's pushing back on you, yes, but there's a problem because you're pushing on the paddleboard, but the paddleboard's also pushing on the water. We have multiple pairs of action-reaction forces, and those pairs of pairs aren't necessarily balanced. And this is where you oftentimes get these interesting, like I said, fail examples. Stepping out of a boat in motion is a great example of a Newton's third law fail. That happens quite a lot. But here's some other ones that are on here that aren't really fails so much. And I'll mention on the skateboard is a really good example of this one. So with a skateboard, if you think about it, if you're pushing on a skateboard, right, you're pushing forward, it's kind of weird to think what happens. You actually push backwards, but the skateboard moves forwards. How's that even possible? These are these action-reaction pairs. I'm pushing on the ground's pushing on me. I'm pushing on the board, and the board is pushing on me. So there's actually two different things that's happening. There is literally an action-reaction pair here, and there's an action-reaction pair here. And what happens is that the amount that I'm pushing on the ground is greater than the amount that the board is pushing on the ground, and you end up sliding forward. So action-reaction pairs. And again, all I'm trying to get you to do, I'm not trying to confuse you, but it is confusing, is to kind of start thinking about if I'm going one way, something's going the other way. So for example, our space shuttle here, this is one of the Falcons, taking off. The Falcon's pushing down on the ground, and it's causing it to move upwards, equal and opposite. right? These things called a Newton's cradle, believe it or not. I have one of these in my classroom, right? When this ball comes in this way and hits, eventually you've seen it, this ball is going to move out this way. Well, why is that? Because of force pairs, that you have equal and opposite reactions that are happening. This one's going to kind of bounce. This one's going to end up bouncing against each other. And eventually that one's going to get pushed out the other side. So it's kind of an action reaction pair. And then it'll come back the other way. And then, of course, my favorite, Granny, epic Granny. Granny in a wheelchair fires a machine gun. What's going to happen to Granny? Granny's going to shoot this way. She's going to create so much force that eventually Granny's going to roll that way. That's called recoil, is a really common, COIL, really common example of Newton's third law, where you're pushing something one way and you end up moving the other way. And the last example I have down here is my frogs in space. If you ever get a chance to see this, they took a poor frog up onto the space shuttle and let this poor dude try to swim around. And this is what happens when you have things that are used to certain action-reaction pairs, and those action-reaction pairs are taken away. That's actually what's happening on the skateboard, on the paddleboard as well, is that you're used to certain things like friction and air resistance being there. And all of a sudden you lose one of those pairs of reactions, and all of a sudden things don't work. And this poor frog's sitting there swimming away and he's not getting anywhere. And he's just kind of going like, why? And he's very confused because he's used to pushing on one thing and having it push him forward. And yet he's pushing on the vacuum of space, and he doesn't get that reaction pair because there's nothing to push against. So anyway, if you get a chance to look up frogs in space, it's humorous, but I feel bad for the frog. So there you go. Taking a look at some of Newton's 3 laws and how they sort of apply to motion. In the next one, we'll get into more of the math. So we've got Newton's first law is inertia. Newton's second law is F equals ma, force is mass times acceleration. And Newton's third law, for every action, there is a reaction. All right, I'll see you in the next one for math. Get your calculators ready.